So what we're going to be working on is looking at Coulomb's law today. So Coulomb's law was introduced in class yesterday. We introduced it just as an algebraic equation. So here is the equation that Charles Augustin de Coulomb, I think I said, yeah. That's the equation that he came up with in 1785, according to general physics. That force is the force on object 1 due to object 2. It's a vector. When I tried to rework this, something's wrong with my update of Microsoft Word, and now it doesn't show vector signs, it shows V's instead. So it showed F with a V over it. And so I actually used last year's instead of the one I was working on so that it would have the force right. Just in case you look back and you say, wow, those are exactly the same slides as last year. Well, there's a good reason for it. So the force vector, the minus sign, of course, is just to keep the direction straight. You have a constant out here, 1 over 4 pi epsilon 0. Depending on where you are and what you're reading for your sources, you'll see it written either the way on the left or the way on the right. The difference is the pink parenthesis there, 1 over 4 pi epsilon 0, is defined as K. K is a universal abbreviation for constant. Epsilon 0 is an important physical constant. It's the permittivity of free space. It's what tells you basically about how conductive a vacuum is. Because you can actually make charge go through a vacuum. Oftentimes we think, well, that doesn't seem right. How can we make the charge go through a vacuum? I can't have a hot object here and have conduction over here, right? You have to have something in between. But you can't have radiation in between, by the way, but radiation's a different way. So how do we have a electric charge pass between them? And it's because you actually have an electron that leaves one and goes through nothing and gets to the other one. So that permittivity of free space, it's on my next slide, it's a fundamental constant. So the value of that permittivity of free space is, this way here is the easy way to remember it. 1 over 4 pi times 10 to the minus 7 and it times the speed of light squared. C is a new symbol to you, but it's one we're going to use extensively this semester. C is the speed of light in vacuum. And so that's a pretty easy one to remember. Numerically, it comes out to this crazy long number, 8.85 times 10 to the minus 12 is all I have memorized of it. Coulomb squared per Newton meter squared. And so the force constant K sub E is 8.99 times 10 to the 9. It's just a whole bunch of nines, right? 8.99 times 10 to the 9. Newton meter squared per Coulomb squared. So in this equation, and it is always important to note, I have newtons on top, meters squared on top, Coulomb squared on bottom. Multiply that by Q1. What does Q stand for? Charge with units of? Units of coulombs. C. A volt we will talk about later, but it's an energy per charge is what a volt is. So multiply it by coulombs times coulombs. That'll cancel out the Coulomb squared on bottom. Divide by radius squared, divide by meter squared, we'll cancel the meter squared on top, and we have an answer, force in newtons. It's kind of important to get our units straight. If they did come out to be a force in newtons, we would wonder what went wrong. So that's what you learned in class yesterday. And so when you go and do the homework, you're going to have lots of problems doing that. What was that?
Do we have different homework problems?
You do occasionally, not for this first assignment.
I mean, last semester, I think it was like the last few assignments that happened.
I don't know how many, but occasionally you'll have different problems. Usually it'll be all the same, but one if it's different.
Everything else is just the same as physics 251, like the schedule and then the homework, everything is the same.
Yeah. It's just your homework assignments might be different. There is one additional homework assignment, which is one that is assigned today. And after today's lecture, you'll be able to do at least the first 2 problems. there's, I think, a total of 7 problems, and you won't be able to do the rest of them until after next week's lecture. So that assignment's a 2-week assignment.
So it's not a expertise, but it's just a different side.
Correct. So it's called HWC1 for Calculus 1. It's the only additional one, so there's no C2, but Okay, so we talked about the general physics approach. Now let's get to the calculus approach. The calculus approach, the more fundamental approach, the one that allows us to deal with real situations. Because Coulomb's law, the way we learned in the algebra class, is technically only true for the force between 2 point charges. And so, what's a point charge? Well, in truth, a point charge is a charge with no volume. That doesn't actually occur. Maybe electrons are charged with no volume, maybe not. But usually we have charge spread out over something. If the distance away from the object that's charged is large compared to the size of the object, then it's a really good approximation to treat it as a point charge, and this is going to work. But if it's not, then you have a problem. Except for in the case, and I think we worked out Newton's synthesis last semester when we were talking about universal gravitation, and we did, because we talked about the force of gravity. If you're inside of a shell, doesn't matter where you are, if you're inside a hollow shell with even mass distribution, the force of gravity on you is 0, because the different directions and magnitudes add up to 0. We can use the same thing for Coulomb's law, because it's once again an inverse square law. It's exactly the same form, so that Newton's synthesis still works. So if you have a spherically symmetric distribution of charge, you can also treat that as a point charge, and Coulomb's law will work. Anything else is going to be more complicated. So if you have a single point charge and you want to find what's the force on this single point charge due to this charge all spread out over there, then I'm going to have to add up the force from each piece of charge. And how do we add up the force from each piece of charge when it's a continuous distribution of charge? We integrate. Hence, physics with calculus class. So here's the differential form of Coulomb's law, the form that you're going to use in that HWC1. So dF, this is a vector note, is equal to minus KEQ1, because we're using this to find the force on charge 1 due to the charge distribution dQ. Because it's very important to keep the vector signs here, I have 2 forms, either r hat over r squared. So r hat is giving us the direction. Remember, there's no magnitude to r. Well, the magnitude of r hat is 1. There's no change in magnitude. And then over r squared for the distance squared. Or if you like, you can put r vector over r cubed. R hat is equal to r vector over r. Hence, they're exactly the same in meaning. It's just different ways of writing it. One may be more convenient than another as you're solving a problem. So we are going to have to take this and determine what is dq. Now, calculus, what's the meaning of dq? In this case, it's not a change in. It's simply a minute amount of charge. We're going to take that dq and we are going to say, okay, I want to get this dq into something spatial. So I want to get it to something that's a number times a dx if it's linear, times a dA if it's an area, or times a dV if it's a volume. And so I have like 3 steps in how to solve the problem here. And the first one, oh yes, I was like, that's not the way it was. That's because I didn't use the one that I prepared for today because of the vector signs. So it depends on our geometry. If we have a one-dimensional problem, that is if the charge is spread out over a line. And we can use this if the line is curved as well. In fact, in my first example, I'm going to use a curved line. Then my dq can be the charge per unit length times ds, the length, a little infinitesimal piece of the length. And so lambda there, the charge per length, or lineal charge density, is something you need to determine. Now we're going to do today simple cases where the charge per unit length is constant. It's certainly in real life more probable that the charge per unit length is not constant. You know, bigger charge per length here, smaller charge per length there because of changing electric fields or something. But we're going to make life easy. We're going to just use a constant charge density so that that lambda is going to be a constant. That makes it easier because when you're doing integrals, of course, constants are not a problem. If it's charge spread out over an area, so for instance, if I'm talking about this globe, it has a surface area. And so then I would say my dq is mu, the areal charge density, that's charge divided by area, multiplied by dA. What would dA be in Cartesian coordinates? dx dy. Cartesian coordinates is the x, y, z. And so it'd be dx dy in Cartesian coordinates. If you use different coordinates, you need to determine what's going to be in those different coordinates. And then if you have a three-dimensional charge distribution, like a normal object, and we'll have to learn later, only in an insulator really, because in a conductor, all the charge is on the surface. Then you have the charge density rho, same as mass densities, just electric charge density instead of gravitational charge density, dV. And once again, in Cartesian coordinates, that'd be dx, dy, dz. So the first thing you have to do is consider your geometry and make the appropriate choice to substitute for dq. The next step is really, really important. Break your df into components and solve each component separately. Now I say that, and in the first one, I'm going to use an argument that I don't even have to do an integral. But in many cases, like in the second one, your life becomes a whole lot easier if you remember that I can just do the x components, do the y components as separate integrals. So let's just get right to it. My first case, a circular arc of charged wire. Not a complete circle. If I had a complete circle and I wanted to know the force at the center of that circle, what would the answer be? It'd be 0. That's why it's not a complete circle. So what I'm going to do is have a circular arc. So there's my best rendition of a circular arc. And here's the center of that circle. And so I have a radius r. And this wire is a length L. And it holds a total charge of Q. So what is the first step I should use in trying to solve this to find what the force is on a point charge? Okay. Consider the force on a point charge of Q1 here due to a charge of Q2 spread out evenly on that wire. So the first thing to do to find the force on charge 1, let's just start with Corso, and I'll just cycle like that. So Corso, what's the first thing to do? To solve for the force on charge Q1 due to the charge Q2 on what? The wire. Aside from drawing the picture that I already did.
I was going to say that. Determine the force.
That's what I want to do. Well, I heard determine the force. And what's the first step to determine the force?
List all the forces that.
Not going with that.
Okay.
But you were saying something, Gila? And you come up logically next in line.
Determine the DQ.
Determine the what?
The DQ.
Okay, determine the DQ. That's right. So our step 1 is, okay, that's supposed to be a 1, but it didn't look like it. Step 1, DQ equals. Now, determine the DQ. Which of the 3 types of charge distributions do I have here? Linear charge distribution, an areal charge distribution, or a volumetric charge distribution? Linear. And so that means it's going to be equal to lambda ds, where ds is a little piece of the wire. So I'll put a little box here. And that box has a width of ds. Wow. That width is ds. Of course, now I need to find lambda, the charge per unit length. We're told that it's evenly distributed, so lambda is simply going to be the total charge, Q2, over the total length, L. All righty. Next up, Alex, what do I do next?
What's the whole equation?
What's
The whole charge force equation.
okay? That's
Where can I see it?
you can see it right there.
Are we supposed to break up the DF components?
Yep. Okay, so we're going to take the DF. Now that we substitute for DQ, we're going to break it into components. So I am going to set a coordinate system so I can break it into components. And I'm going to set my coordinate system in the simplest way possible. First, use a symmetry argument. What's that symmetry argument? The R is constant. And so that means my DF, and I'll write this down. Has only one variable in it, right? ds. Oh, forgot one thing. R hat. Ah, shucks. Why do I say ah, shucks when I put R hat in there?
Well, how did you get that equation?
That's the one that we had two screens
you
up.
haven't broken anything up yet. We just copied it.
Yeah, I just copied it except for I took the left-hand form and I replaced DQ
Right. No.
with our lambda ds.
So we haven't broken anything up yet.
Nope. So why did I say oh shucks about that R hat?
Is it another variable?
It's not a variable, but the direction changes depending on what part of this you're on. And so the force directions change. Yes, I'm going to have to break into components to figure this out. So let's start the component idea off by first identifying what direction. Let's say Q1 and Q2 are both positive. If they're both positive, is it an attractive or repulsive force? Repulsive. So what direction is the force on Q1 due to that charge? Directly away. So it's, oh man, my hand just keeps moving stuff. Yeah. New color. It's going to be light blue, apparently. So there's the direction of DF. It's almost the same direction. That's better. So there's my direction of DF. Now I need to break it into components, and I'm going to choose my components as you probably would think I should. X goes like that, Y goes like that, with my Y pointing straight to the center of the wire. I point straight to the center of the wire so I can take advantage of symmetry. Because if I have Y going straight to the center, then I'm going to go equally to the left side as I go to the right side. And so when I add them all up, as I go across, my DF is going to go from down and to the right as you see it now, to down to the left. It's always going to be down in the Y direction. But in the x direction, it's going to go from left to right. The magnitude's always constant. The amount of, for every position on the left side, you have one on the right side. So the horizontal components have to add out to 0. So I chose to choose my symmetry so I can break this down so only one component's not going to be 0. So I have my x and y components. So I would have r hat equals, and I need to define an angle. I'm going to define the angle with the y direction as theta. And I'm going to make it so it's a positive angle if it goes this way. So if I was looking at this piece, then I'd have a positive theta. And so r hat is equal to x hat. Looking at that triangle, the opposite side is the x component. And so that would be r hat sine theta, or x hat sine theta, plus, that's plus sine, plus y hat cosine theta. Now that would be my r hat direction, except I need to reverse the signs out front for the simple reason of, instead of pointing up like I drew in my arrow, my actual force vector is down in the bottom. And so there's my components for r hat. Now I have theta as the variable in r hat, and what was the variable in my integration? Well, the d what? ds. So I have a variable of s, and now I have theta. So now I have two variables. And so now any genius says, well, you really screwed up. df vector is equal to minus k q1 lambda over r squared times ds times, I have a sign error somewhere, you know that? You know how I know I have a sign error? Because I should have negative for, anyway, x hat sine theta I kept myself consistent with the signs I had. Maybe they'll come out and I didn't have an error. I just made a mistake in thinking I had an error, but here's what we have. df has this equation, variable s here, variable theta there. I immediately can break this into components, so I can put x component and y component So now I've broken it up into components, and I have to go ahead and do the integration, but I have two variables. Good.
So how can we do that? Like, I've never broken it up into components like that before, at least not with an addition up there. Like, that whole process is confusing.
Okay. So I used just the distributive property.
Right?
So I just distributed out, so I had k q1 lambda over r squared ds x sine theta.
Oh, yes, they're still
plus,
added together. We just
yeah.
find them. Okay.
Yeah, so this is just the x part of it and just the y part of it. And so my df vector
Right.
is
Still
x hat dfx plus y hat dfy.
Okay.
Okay, what I thought you were going to say was, how do I do this with the theta and ds? I have to look for a relationship between theta and ds so I can combine them to get only one variable. It has to be possible or I cannot do it. So we come back and just look at the geometry, and we know a given for geometry is the length of arc S is equal to theta times the radius. That's a given relationship for any circle. Arc length is equal to theta times radius. So I can just take derivative of both sides. ds is equal to r d theta. So I just put that in over here, and I have this is equal to k q1 lambda over r squared times sine theta r d theta. Life is getting simple again. How do I find the total forces? Let's stick with, well, let's do the one that I said has to be 0. We're going to go force in the x direction is equal to the integral, and I'll have to put my limits in. Notice r over r squared is just going to be 1 over r. K q1 lambda over r. Actually, let's put that outside of the integral sign. Integral sine theta d theta. What are my limits for the integration? I'm going to go from an angle over here that has the arc length is L over 2. So I'll have theta minimum equals minus arc length of L over 2 divided by the radius. Right, that's using this equation. Solve it for theta. Theta is S over R. So the arc length on the left side of center is L over 2. It's minus because of the direction. So that's equal to minus L over 2R. And if I go to the other side, to the maximum angle where it's positive, what is the arc length on this side? It's positive L over 2. And so the angle is going to be L over 2, positive L over 2 divided by R, or L over 2R. So my limits are from minus L over 2R to plus L over 2R. Now, we're all pretty astute students. I know I've had you in class one semester already. You may or may not have learned about integrating symmetric and anti-symmetric things. Have you learned about that? Okay. Well, sine is an anti-symmetric function. What that means is sine of theta is equal to minus sine of minus theta. Usually we say sine of minus theta is equal to minus sine of plus theta. It's anti-symmetric. Let me draw a graph to illustrate that. So here's the origin 0, 0. A sine wave goes like this. It's anti-symmetric about the origin. That is, if I go to the left, I go down. If I go to the right, I go up. And it's exactly the same amount. If I go left this far, I'm going to go down this distance. Go right the same distance, I'm going to go up the opposite distance. So they're anti-symmetric. In that case, then an integral is the area under the curve. And it's going to add up to 0 if you have a symmetric limit with an anti-symmetric function. So because we have symmetric limits, this has to be 0. It just has to be 0 because of it being a symmetric integral. Now, if we want to go ahead and do the integral, we can. What's the integral of sine theta d theta? So that's equal to K Q1 lambda over R times minus cosine of L over 2R minus a minus, so plus cosine of minus L over 2R. But because cosine is a symmetric function, the even function is actually the term we use. Because it's an even function, cosine of L over 2R is equal to cosine of minus L over 2R. And so these here add up to 0. So yes, it comes out to 0. I could have just explained it away at the beginning based on the symmetry. I could set up the integral, and then I could explain it has to be 0 based on the symmetry of the integral. Or I can go ahead and work out the integral and find out, hey, it comes out to be 0. So that's the trivial one. Now the non-trivial one. We have dfy is kq1 lambda over r squared. Cosine theta r over d theta. Once again, I'll cancel one of the r's. So I'll cancel one of the r's. And I'll have the force in the y direction is equal to the integral of this. Once again, let's put the constant part out first. Cosine theta d theta. So now I have to integrate cosine theta d theta over those limits. And so what's the integral of cosine theta d theta? Okay, it's going to be sine theta. And so this is equal to kq1 lambda over r times sine of L over 2r. I intruded, my bad. But we just said sine is antisymmetric. It's an odd function. And so sine of minus L over 2r is minus sine of L over 2r. So it turns out that this thing in the brackets is just equal to 2 times sine of L over 2r. Now let's look back at our geometry. Can we figure out what sine of L over 2r is without doing much work? Sine is going to be the opposite over hypotenuse. And yeah, pretty much no. So I'm just going to leave my answer at this. And now I have to acknowledge I made a sign error. How did I make a sign error? I'm sure it was right at the beginning. Obviously, I noticed I had a sign error right at the beginning. But we know that the force y is downward because it's being repelled. One last thing I didn't do, I have lambda. I should substitute back in lambda. Lambda, we said, was the charge 2 divided by the length of the wire. And so there is our full answer for in the y direction, except for it's going to be negative, not positive. Now, overall, if you understand what I did, you could have done that thing real quick. Of course, I did it in a long, drawn-out fashion because I want to make sure we talk through every step of the way. Now, this next problem is exactly what you have for problem 1 in homework C1. None of you have a computer out, so I'm not going to have you look up homework C1. But homework C1 says that we have, I say it's exactly, there's one difference. Homework C1 says you have a semi-infinite wire. Any idea what semi-infinite means? It's what?
It's where you pretend it's infinite.
That's half infinite.
It's half infinite. What half infinite means is it has one end only. It starts here and goes on forever. Does semi-infinite exist? No, you can't make a wire that's semi-infinite. But it's reasonable to do the problem because what you're saying is it's a wire that goes really far away. It starts here and goes really far away. And so, if it goes, if I'm 2 centimeters away from the wire, if it goes more than 2 meters away, I'm probably going to say that's close to infinitely far away. Mathematically, it's not going to make much difference. So it depends on how close you are to the end, how far it has to be. And so the problem is just saying, okay, so take the case that you're close enough that its length appears to be very far away. And so consider the force on a point of charge Q1 due to charge Q2 evenly distributed over a straight wire of length L. Doesn't give you much geometry there. Let's start with the easy geometry, and then we'll go to the harder geometry. So what's the easy geometry? The easy geometry is, here's my wire. There's Q1. This here is Q2 that extends off toward infinity. And we'll put some distance between these that I'll just call A. So it's all in a straight line. How to solve this thing? What's the first step? Come back around to Corso.
Why are we doing these?
Well, we're doing
It's a
these.
small class. Getting exposed. So how do we start?
Yes. What's the first step? It's the same question you had last time.
We write the DQ or
Okay, we start by we have to find what DQ is.
big stealer.
And so we look at this. In this problem, it doesn't go off to infinity. It goes to a length L. I was like, wait a minute, I can't do it. Yeah, that's because this problem is, that's the one thing that's different. We have only a length L. So what is dq if we have a charge Q2 evenly distributed over a length L? Lambda ds, where lambda is equal to Q2 over L. Now I identified a ds. What does ds mean? ds. S. It's a piece of length, right? It's a little confusing because what symbol do you use for piece of length? Sometimes we say dl, sometimes we say ds, sometimes we say dx, sometimes dy. You have to keep in mind what it is we're talking about because the symbols aren't always quite uniform. Why is it using ds? Because this could be a curvy line, in which case it's not going to be a dx or a dy because x means along the x-axis, y means along the y-axis. It's not going to be a dr because r means along the radial axis. We've got to use something else. And so dl or ds are the two options that are commonly used in that case. So I recognize a potential for confusion there on what the ds is, hence me making sure we're clear. So I have a little piece of wire ds. And that's done. Gila, what's step 2? Okay. Let's break that baby into components. What direction is the force on Q1 due to Q2? Okay, well, she said x. We're just going to go ahead and define that as the x direction. So my d force vector is in the horizontal direction. We're just going to call that the x direction. I'll go ahead and call this the y direction. But you know what? There's nothing going on in the y direction, so I didn't even need to define it. I just did that to make it clear that I'm defining directions. So it's already broken up into directions. dfx is equal to k q1 lambda over, I better use a lowercase r this time because it's changing, r squared ds. Okay, I have r and s, two different variables. I need to combine to have just one variable. So how do I relate r and s? What?
Is it the S equals 1?
I am simply going to define S and R as the same thing. That is, I'm going to say that S and R are both starting here, measuring this direction. So I'll put S comma R. Because the R has to be that. The R is the distance from my point to where my DS is. So that's got to be pointing that way. And let's just make S the same thing. So DS is DR. And I am now able to, and because I'm just willy-nilly making my directions, I could once again have made a sign error. That's why it's really important to, in the problems, it has you draw the DF vector first. Why? Actually, the problem has you draw the DE vector. I told you can start this after today's lecture based on what we learned. DE is just DF divided by Q1. So you're just getting rid of the Q1s and you have the same thing. So you draw the direction so you have your direction straight. So in the end, if you end up with something that doesn't make sense, you know, well, I made a mistake there. Because it's easy to make these mistakes. I'm pretty sure I've made 2 of them. Let's move on. So I am just going to make ds is dr, so it just equals k q1 lambda dr over r squared. So f of x is equal to the integral, well, let's put the constant first. What is the closest distance? The closest distance is A, and what's the farthest distance?
L. A plus
A plus L. Okay, so we just do this integral. What's the integral of 1 over r squared dr?
R and
It's
So you bring down the minus 2,
yeah.
and then you
Raise
raise it from minus 2 to
minus 1.
minus 1.
So it'll be minus 1 over r. Minus 32. Yeah, it's out. What the hell?
All right, now we can look at this and we can say, hey, look, it has the same units as we had before. That's probably a good thing. The force should always have the units of newtons, the same units.
Are we supposed to be dividing by negative?
Yeah. You're divided by -3, aren't you? I did the derivative rule instead of the integral rule. You
No,
div-
it's negative.
You divide, or minus 1, I mean, minus 1. You divide by the new power. In my head, I was saying 3 for the same reason I was doing the derivative rules in my head. So you divide by -1. Thank you for correcting that. Because otherwise we get off by factor 2. And I feel stupid when I go home, sit down and say, oh, wait a minute. Okay, so now we do this and we have minus k q1 lambda times 1 over a minus 1 over a plus L. And now, did I make a mistake? Yes, I did. What was my mistake? It was with my directions. Because now, once again, I have a negative answer when the answer should have been positive. That's why I made sure I knew what direction it was supposed to be to begin with. So if I make a sign error, what was my sign error? I should have called those negative distances.
does the force equation have a built-in negative?
It does. Didn't I put that in? Oh, you're right. I forgot to put that in. That changes everything. Look, now it's going to be right-o. Okay, so this is our answer. That's as far as you can go with it, except for with the substitution K, Q1, Q2 over L. I guess you can give it a common denominator. You might consider that nicer. Actually, we'll probably consider it nicer. Yeah, I can cancel out that L, can I? Yeah, this is a simpler looking form. So that's our simplest form. So, got our answer. That was only in the x direction. What about the y direction? There was never a force there, so there's nothing to calculate. You can't, I mean, you can say, okay, integral of 0 is 0, but yeah, that would be silly. So that was the easy case. Hey, look, we're out of time. Don't have time to do the hard case. What's the hard case? Instead of being in line, what if our point was over here? So I will pick up with that next Tuesday.